Anyone wants to submit late homeworks? You were waiting so badly to have a new homework, So you have already got an idea how pleasant are homeworks, and I think as time goes by, you support me more and more than doing some part of the things for this course in computational form is better. It's more pleasant and less challenging. So on coming Friday, we are doing presentations. We, meaning you. And I have summarized your goals. So if you are not super happy with distribution, welcome. Send me an email. And the plan is that since we have about a dozen presentations, and we want to please everyone with chance to answer questions. Plan to be for like 3, maximum 4 minutes. So it's not very many slides. And just go over. Well, the best thing, since it is not very challenging, you can just go over the MATLAB manual, try your, just install it on your laptop and try things and share your experience with your peers. But other option is to, if you were missing Wednesday labs, you can just stop by to catch up or watch recordings, right? The stuff are recorded. Yes. So here are labs from this year, and if you are curious what is in the future, it's recording from last year. And today we are about at this bar in the class material. So here are your votes. I throw in something like for Ben, because otherwise this is too simple. And it's mostly based on what you expressed as you usually say. So homework number 3 is not too challenging. It can be some amount of writing, but it is based on class material. I will also make comments on Wednesday night on what to do. So this is implementation of the bridge, how to find observable that we are going over. This is just going over class material. This one is kind of a little mathematical challenge, but if you are taking or were taking differential equations, it is like 5 minutes. If you're not, it is 15 minutes. And I will go over in Wednesday night. And this one is truly challenging. So everything else is 100 points, and this one additional, let's say, 30 points, because it took me an hour for the first time to do this one. Although, well, stop watching, tell how long it will take for you. We have already explored the German money, right? Was one of the subjects in previous meetings. What? No. It's better. And today we are going to explore German postage. So they're kind of crazy about glorifying scientists, and one of the postage. So there is a phase of Heisenberg. You remember about last week we looked at the uncertainty relation, right? And Ben did excellent formulation of this principle that position and momentum can be determined absolutely correct, certainly. So there is an uncertainty. And this idea did propagate from circle of professional scientists to a circle of general public, same as like Einstein relativity or Schrödinger cat. And here's the commonly flower with many petals. And you know this guess, like when we think about your beloved one loves, doesn't love, loves, doesn't. So here's position moment, position moment. And here he's at his ages. When he was younger, he was more happy. So this is a question that we went over last meeting, right? But the original Heisenberg equation of motion is for the operators. But we are going to put brackets. So not for operators, but for expectation values of observables, right? So if you are suddenly coming here for the first time, here's a summary of what we were doing for the previous month. We promise everyone right in the syllabus that it is physical chemistry course, but in fact you cannot do physical chemistry and predict outcomes of measurements by picking instruments without knowing quantum nature of electrons. And if you are looking on quantum nature of electrons, you cannot do much without some chapters from calculus differential equations and linear algebra. So we are covering several things. And we are predicting future. There are several ways to predict future in sense of electron, of the wave function, which is generates probability distribution of where electron is if you take it absolute value square, or it can help to get the expectation value of measurement. And one of the ways of predicting future is just multiply wave function of the past by evolution operator and get evolution operator from the future. Another one is to practice our protocol to solve time-dependent Schrödinger equation. Or new formula is Newtonian. First, solve time-independent for wave functions and energies. Then you take the wave function of the past and extract initial conditions and form expansion coefficients. And then you construct future as the superposition of wave functions weighted by expansion coefficients with phase accumulation factors where phase accumulation depends on eigenenergies. And then when you have found this wave function, you take on left, right, put operator inside and get the outcome of a measurement. Last time, if by some reason your Friday was more busy than optimal, we covered so-called Heisenberg equation of motion. Here, wave function is a complicated object, right? But if you need only one number or one trajectory on like set of numbers for each point of time for an observable, why do we process wave function? Can we set up an equation for the expectation value only? Yes, we can, and actually it was done by Heisenberg. So based on the property of the operators in quantum theory are Hermitian, and especially Hamiltonian is Hermitian, one can set up how the time derivative for this thing, how the equation of motion for the expectation value of an operator develops in time. And it develops in time according to commutation of this operator with Hamiltonian, right? So protest, object, or ask question if you are happy with this equation. More or less fine. It's not abstract academic knowledge. We are going to practice it. We're going to use it. And another thing that it's becoming very boring if you go over the theories for most of people. So we have a little connection to real life. So we are considering a wrapped electron, an electron that get like consider proton, not proton, the hydrogen atom where a proton was removed, and then assume that there was a initial momentum and some distribution in space. So intuitive expectations that you guys developed were that this cloud of electron will continue somewhere to move if it had initial momentum, and we worked so hard for a week to see that it will blow up, expand its shape, right? But we didn't show that it moves continuously. And there is a reason. It's too expensive. We are already exhausted with practicing integrals that are hidden in this thing. So what we are going to do today is to apply protocol of Heisenberg equation of motion to see if the average position of this electronic cloud will move anywhere. So we need to torture our brains with new theories, but solutions are like 10 or 100 times quicker. Therefore, one develops several tools. Like if you play computer games, you will always have your character that you operate have several weapons, like, to attack different monsters. So same in quantum theory. So if someone catches you at the grocery store and asks, what's the difference between Schrödinger equation of motion and Heisenberg equation of motion? Well, it's probably not very likely, but you can give an answer or just compare them. So Schrödinger equation of motion applies to wave function which has infinite number of degrees of freedom, and Heisenberg equation of motion is much better if we need to track just one observable or maybe a couple of them. Mathematically, Schrödinger equation needs to diagonalize Hamiltonian or matrix of Hamiltonian, which is a big challenge both for analytical and computational things. While for Heisenberg equation of motion, one needs just to solve ordinary differential equation propagated forward in time. So in this aspect, Heisenberg wins. But in the next aspect, whether equations are linear that it includes the unknown stuff only in the first power or derivative. So Schrödinger equation, yes, it's always linear. We do not change it, we change Hamiltonian. But Heisenberg equation of motion can be substantially nonlinear, which is another headache. So therefore, one takes a decision which weapon to use against separate monster again and again. So in each specific case. Again, it is natural if you're tired of the course. And we are coming to a point when we got so many new information that it is so easy to forget it. And the idea that you have some take-home message that you remember years after, right? Which is not always the case. So here is an attempt to summarize what we do in like abstract space of theories. So we can assume several dimensions, like one dimension where we get through different theories, right? Another dimension where we will practice different objects. Right now we have just electron free space, but later on we will have more and more realistic systems. And at the end of the course, we will do really realistic systems. So more realistic. And here is whether the quantum system is allowed to live on its own, or it is perturbed, like if anyone is hammering it or heating or exciting by a laser pulse. So by now, we didn't apply evolution operator. We did apply Schrödinger equation of motion for electron in free space, and today we are going to practice Heisenberg equation of motion for electron in free space. What is Hamiltonian? Does it have kinetic energy? Yes. What is the potential energy in a free space?
No.
Yeah, nothing. So the Hamiltonian is just the second derivative over position, right? And now, from now on, you are not, how to say, irritated by this. Well, maybe you irritated, but it's not a surprise. You have seen this equation. If you concentrate, you probably can reproduce it without any external source, right?
The symbol on the bottom, is that sigma?
No, it's my nice calligraphy for X.
Oh.
So derivative or position. So we are going to practice Heisenberg equation of motion by replacing this arbitrary operator A by position operator. And we are going to finally answer our original scientific question, whether the electronic cloud will move anywhere in average, and whether it will move in just linearly with constant velocity, or maybe it will turn around or do something complicated. Well, the answer is, intuitive answer is nature. Like if it had some average momentum, it should continue, right? But we know that quantum theory offers surprises, and we better prove it more or less rigorously. On one hand, on the other hand, we'll practice this Heisenberg equation of motion. How do we practice it? E d t x equals 1 bar each x, which means we have minus h bar square over 2m, and we put outside of the brackets. Then we have d2 dx squared x. And what does it mean if you have square brackets?
Commutation.
Yes. So what does it mean commutation?
Isn't that like the ha?
Yes, it is haha operator. If you have wait, h comma a, it equals ha minus ah. So haha operator. And now we put regular brackets, but here it is d2 dx squared x minus x d2 dx squared. So we'll put this brackets later. Let's process without them right now. So how do we process this subtraction? I do not know about you. I always feel unhappy when I see such notation because there is an operator, but there is nothing after. So operator must act on something. So we do need to assume in this expression that we have some function that we will just put in for the time when we process the operators, and then we will remove. And if it looks as some function of x, then we can interpret this combination of operators that this one is take the second derivative, then multiply by x, and this one is multiply by x, and then take second derivative of everything, of both product, x times y. Right? Both of this differential operators apply to the function. So once you take derivative and then multiply, and second time you first multiply and then take derivative. So if we take derivative and then multiply, it's simple, trivial, we do not change anything. But if we multiply by x and then take derivative, we probably should focus on this stuff and process it in more careful details. So we practice. First, we do one derivative and then another one. Otherwise, it is too complicated. And for the inside derivative, we practice which rule?
Product.
Product rule, yes. So dx times phi unchanged plus x d phi dx, right?
Is that a negative at the beginning?
No, it's I'm not the first who used the screen, and in the corners it doesn't it doesn't function well. Okay. So we keep the outside. No, I don't need to keep it. I can apply it right away. So last term also it no, we do not do anything else. The first result of chain rule is okay. And now we are applying derivative once again, and there will be total 4 terms. Right? So we will term 1, term 2, term 3, term 4. So ddx applied to dx over dx, which is actually 1, times phi unchanged, plus ddx dx, which is actually 1, times d phi good, plus 30. So now we are applying product rule to the second term. dx, which will be 1 times d phi dx, and last time we keep x unchanged and d cubed by dx squared. Extra points for finding my errors. I hope there are no, but just in case. So this is 1, and derivative of 1 will be 0. Okay? This is 1. This is 1. So we will 2 define dx plus x d to pi dx squared. I'm going to flip slide not forward but backwards to look where we were before. Okay? So we were processing this yellow blob, and then we need to subtract this stuff. X derivative phi. Minus x derivative phi. What do you see? These two things are equivalent, right? X derivative phi. So x derivative phi. And this one is a new thing. So upon you complete your commutation exercise, this will be, how to say, precipitate, result of your mathematical reaction. And our phi function, it was only auxiliary tool. So in fact, we'll forget about this phi and tell that all mutation of position, Hamiltonian and position operator will be equal to 2 derivatives with some factors up front. Make sense? Do not hesitate to protest if something looks strange.
So what will the derivatives be derivative?
Huh?
What will we be taking the derivative of? Is that what we're going to?
No, we are not going to take derivatives. I promised you easy life, and it will be easier than, well, it will be not like super easy. Immediately we all go to the beach, but it will be much easier than diagonalizing Hamiltonians. So, excellent question. What we will apply our derivatives to? To nothing. There will be next step. We will look at this derivative and identify that this derivative is nothing but momentum operator. Okay, so we will roll over through the definition. I anticipate you and you all will enjoy if you do. It is so much easier than diagonalizing Hamiltonian. Well, it's some writing. People call it operator algebra, but it is easy, especially for this case. Okay. Do it again. Okay, so now we can put brackets and we can we are removing this phi operator over there. So the commutation of Hamiltonian and position operator does give you 2 times ddx, right? That's what I was asking. And we are removing this red phi. We are not going to apply this operator to nothing. We can carefully take care of the factors. So a factor of minus h bar square over 2m comes from Hamiltonian. A factor of I over h bar comes from, it will come later. forget about it. So only h bar square over 2n. Now, I do remember that if I remove 2 and multiply the derivative over position by I h bar, it will be definition of momentum operator. So what I'm doing, I then t I more momentum. So we know this definition of momentum operator. And we suddenly realize that by taking commutator, we are getting momentum operator. As a price for it, we need to divide everything by factor, imaginary unit, and h bar. And then we can cancel second power here, first power here. We can cancel 2 here and there. And when we multiply it by the factor up front, we will cancel another Planck constant h bar here and imaginary unit there. I can go to empty page and repeat it if you vote for it.
Please do.
Minus h bar square to n minus 2 t dx. Okay, so it is what we proved by taking commutator.
Are those the angled brackets just like saying they're multiplied?
Angular brackets mean that it is x equals integral I star times x plus I dx. So when we put brackets, it means that we multiply the operator by functions from sides. It is implied, but we are not going to do it. Okay, so let's practice factors. Cancel 2. Multiply by I h bar. And since I want to be mathematically correct, I divide it by I h bar. Now, by definition, this I h bar ddx, it is p with half. So it's momentum operator. And now I'm rewriting it right once again. ddt of x equals h bar minus h bar squared over m. So factor 2 has already cancelled. 1 over I h bar. And here I can already write expectation value of p operator. So I anticipate that all these factors will cancel. H, the second power, h with first power, cancel. And through the operations, I lost minus sign. So it should be, the minus should also cancel somewhere. So I cancel. And this is my mistake that any of you is welcome to find. So this also must cancel. But let me rewrite once again. d dt of x equals p over m. This is really great result. We still have some generous other minutes. This is the bridge to the intuitive expectations. So if we know average momentum, we can find how the average position will change in time without any information about wave function. So there will be one more equation for p changing in time, but I want to rush and get to sweet part right away. So the cost, mathematical cost of solving such equation is the same as for Newtonian mechanics, as for classical science, without any quantum features, right? So you have just one unknown function and you solve the differential equation and find it. Right now, we are in the quantum kindergarten. We are talking about position and moment, but later on, we can go into predicting outcome of NMR measurement or spectra or some other things. So expectation values will be different, related to real life. Here is the simplest possible thing, but we can base this equation is really easy to solve. If you treat this angular brackets x as just one symbol, one function. Okay? Let me illustrate. Yeah, here. Oh, yeah, minus was in the definition of momentum. Credit to myself. No one found it. So here is the equation that we got, and it is really easy to solve. So how do you solve differential equations? You integrate them, if they're simple. So you apply integral. Here t, here tau, formula should be different variables. You just integrate left and right part over time. So if you apply integration to derivative, it will just we come back to the function. And on the right part, well, minus its value at the initial time. And if we integrate the right part, assuming that momentum doesn't change if it is a constant, what is the integral of constant?
Just t or whatever.
Yeah, independent variable. So we are getting that if you propagate in time from time 0 to time tau, then position will be of the center of the wave packet of the electron will be whatever it was at the beginning plus expectation value of momentum divided by mass, which is velocity times interval of time that passed since the beginning, right? Same as like if I'm driving a car with 90 miles per hour, after 1 hour I will be 90 miles away.
So the term plus the PTM is just the initial condition?
Yes, yes, initial condition. And this also, this both. I did skip, there should be second equation for d dt of p, which I'm going to add really quickly. Just in this specific case, it will be equal 0. I will prove it. But generally, in some other cases, it can be more complicated. But if you're taking notes, prepare to listen and then summarize in your own words. What we did in class allowed us to come back from classical theories, back from quantum theories back to classical theories. This set of equations is equivalent to Newtonian equations of motion. And the protocol to convert quantum operators into classical observables through Heisenberg equation of motion is known as Ehrenfest Theorem. Ehrenfest Theorem. It's so complicated spelling of the name that full credit should be given just for reproducing the name. So Ehrenfest Theorem is the pathway how to come back from quantum equations to classical equations. And the philosophical meanings is that classical, traditional theories are limiting case of quantum theories. So if you just practice this Ehrenfest theorem, you can reproduce everything that was done before quantum discoveries. So all equations are hidden in this Schrödinger equation of quantum theory. Upon this Ehrenfest theorem transition, one can reproduce them. Okay, returning back, I did promise to show that that time derivative of expectation value of momentum will be 0. So dt of p will be I h bar commutator of h and p, right? And h is this factor times p squared, right? So here we practice commutation of p squared and p. So p squared p minus p squared. Instead of p squared, we can write p minus p. It's clear that it will be 0, right? So if time derivative, so we already get that time derivative of expectation value of momentum will be 0, right? Therefore, if we integrate left and right part, so it's too simple and quick, but I'm going to slow down and verbalize it. So here we practice Heisenberg equation of motion, where instead of arbitrary operator A, we plug in operator of momentum. At this point, we do not need even to remember differential form, how it is defined through derivative. We know that if operator is a power of two operators are powers of the same operator, they will commute. We already did show that. So by plugging this momentum operator into Heisenberg equation of motion, we obtain equation of motion that tells that change of momentum equals 0. And if we just practice our mathematical skills to integrate it, on the left part, it will reproduce dependence of momentum on time, and on the left side, it will be 0. Right? So change of momentum of time is 0. Therefore, it will be the same as it was set up initially. So if if the electron is in the free space, universe where there is nothing except this electron, it cannot collide with anything. There is no reason to change momentum. So it will continue to move as it was. So both of your original hypotheses were proved right. First, that it moves continuously according to its momentum, and second, that it blows up. It changes the shape, not shape, changes the width. Yes. So it was skinny and it's becoming fat. Done? So I'll stay here to answer questions, but we're done for today.
On the homework,
Yes?
the last question is cut off.
No. It was handwritten and then I retyped it.
And the stuff.
All this.
Okay.
So the last is just to practice sine x times x times sine 2x.
So that's not convolution. That's multiplication there.
Yeah.
Okay.
It's like three functions. 1, 2, 3.
I don't know. I'm
still playing on the way back.
What?
I said I'm still playing on the way
Maybe maybe Mark. Oh, you don't have the account. Maybe Wednesday.
I'll try and get another third YouTube.
What? We do.
So if we figure out how to do integrals on
section
MATLAB,
tomorrow,
we
section.
use MATLAB to solve the extra credit question.
Yep.
Yeah.
Well,
we can,
if you will not the full extra credit, but you will be some
for now.
right?
And then 10 was due like Thursday,
He
right?
was like, or whatever. You
Yeah.
can always do an extension. Don't worry.
You can
All right.
always just talk to him and be like, oh.
Yeah.